This video is also a continuation of the previous two videos of group theory. So here you can see in the next question I have written, let X be a non-empty set and Px be the power set of X, and then we have to verify whether Px is a group or not under the following compositions as defined by different structures. So here you can see in the first part the following composition states that A star B, this is equal to A intersection B, where A and B belonging to power set of X. A star B in the second part is equals to A union B, where A and B are two elements taken from Px, that is power set of X. That means X is supposed to be the universal set like this. A star B is equals to A del B. A del B means symmetric difference between A and B, that will be A minus B union B minus A. Now in the first case, whenever A star B is equals to A intersection B, let us try to verify all possible axioms. We all know power set of any set will contain all possible subsets of that structure, so that we can say P of X will contain all possible subsets of X. Now that part should also include the null set, and hence you can say whenever you are considering A intersection B, the structure is also a part of what? P of X. So technically we can say this is nothing but a closed structure. So operation star is closed on P of X. Also we know intersection as well as union, both of them are associative, so star is also associative. Now we can understand X, that is the original set itself, is a member of power set of X. So if I want to say A star X, that will be what? A intersection X. Which one is larger? X is the larger part, so intersection will give you A. Similarly X star A will also give you what? X intersection A. From here on again you will get A, and this must be true for all possible structures belonging to P of X. So we can say X, this is the identity element present in this power set of X. Now finally, for any two sets, we can say A and B belonging to power set of X, it is impossible to consider A intersection B is equal to X. Why? Because intersection of two proper subsets will give you a smaller subset. It can never be equal to the original structure, and hence you can say intersection of two subsets of X can never be equal to X. So A intersection B should give you the identity element which is supposed to be X in this case, but here you cannot get any identity structure. So inverse element does not exist in the first composition, so star does not form a group with respect to A intersection B. So in case of intersection, it is failed to become a group. Now moving on to the next one, A star B is given by A union B. So union is also closed and associative, just like the previous expression. So star is also closed and associative. We have nothing to prove. Now what is the meaning of null set? If you consider A union phi, that will be A, and phi union A, that is also equal to A, and this is trivially true for all A belonging to power set of X. That means null set is the identity element. As you can see from this structure, it is the left identity as well as right identity. Now let us take any two arbitrary elements A and B belonging to P of X. Now if I want to find out A union B, because both of them are supposed to be non-empty, it is impossible to get A union B is equals to the identity element which is supposed to be null set in this case. So here again you can see identity element can never be attained. So in this case for two non-empty structures. So here you can see the structure fails to give any inverse element, and consequently Px comma star with respect to union is not forming a group. So in the second case also it is failed to be a group. Now moving on to the third one, A star B is equals to A del B. Del, that is symmetric difference. Remember the structure. A del B is actually given by A minus B union B minus A. So it is trivially closed and associative. So star is also trivially closed and associative. And if we choose B is equals to null set, then A del B, in this way if you want to calculate A del phi, that will be A minus phi union phi minus A. Now A minus phi means it is a part, any element is a part of A, but it is not a part of phi, so result is A. But phi minus A, anything which is a part of phi, it is not a part of A. This is absurd, so the result will be phi. So you can see the result is, final result is A. So whenever you are operating phi, you will get A. So A del phi ultimately gives you A. Similarly, if I want to find out phi del A, what is the meaning? A del B is equal to this, so phi del A will be phi minus A union A minus phi. So just like before, the first part is also phi, second part is A, and so that the final result is A. So for all A belonging to P of X, you can see phi is the identity element, null set. Now we need to find out the inverse element. So if we want to find out inverse element, we can use the definition A del B should be equal to identity. Now what is the identity? Identity is phi. So A minus B union B minus A should be equal to phi. Now union of two structure is phi. That means both of them should be equal to phi, and hence you can say A del A minus B is equal to phi, B minus A is equal to phi. So only possible structure is what? Actually A minus B is equal to phi means what? You are choosing any element from A, but it is not a part of what? B. So A is a subset of B. Similarly, you are choosing any element from B, but it is not a part of what? A. So in this case, you can say what? It is a part of B, but it is not a part of A. Just observe this figure. I am saying this one and this structure. So any element which is taken from X, from here, it is a part of A, but it is not a part of B. So A difference B, for this particular structure, you can say this type of diagram is valid. So this means B is a subset of A. Similarly, for this particular portion, you can imagine this is B, this is A. You are choosing any element Y from here, so it is a part of B but not a part of A. So you can see from here A is a subset of B. So ultimately B is a subset of A and A is a subset of B, so that you can say A should be equal to B. It is not like that A minus B is equal to 0, so that A equals to B. In this way you cannot say A equals to B. You have to use the concept of subset, so that you can say A must be equal to B. So A del B is equals to phi implies A equals to B. What does it mean? A equals to B means if we claim B is the inverse of A, in this case you have seen that it is self-invertible. Why? Because A and B are identical. So we can say each element of Px is self-invertible, and also the same thing is true for phi, because phi del phi, that is also equal to phi, and hence you can say Px forms a group with respect to star whenever star refers to the symmetric difference. Now moving on to the next problem, we have to show that the following set D of all possible odd integers forms a commutative group with respect to the following composition A star B, that is A plus B minus 1. Now A and B are both taken from D, both of them are odd integers, so A star B, that is A plus B minus 1. For instance, you can say A equals to 3, B equals to 5. 3 plus 5 is even, because 8 minus 1, that is again odd. So A plus B minus 1 is also odd whenever A and B are odd. So A star B is also a member of D. That means whenever A, B are members of D, A star B is also a member of D, so closure property is satisfied. Now we have to verify for associativity. You can easily understand A star B star C, where A, B, C are taken from D, can be written as what? A plus B minus 1 star C. Now say this is X, this is C, so X plus C minus 1. So actually X is what? A plus B minus 1. So A plus B minus 1 plus C minus 1. Actually you can write in this fashion: A plus B minus 1. You can see this is the first element, plus C minus 1. So from here on you will get this structure. Also, if we want to find out A star B star C, that will give you A star B plus C minus 1, then A plus B plus C minus 1 minus 1, which gives you A plus B plus C minus 2. So for all A comma B comma C belonging to D, we have obtained A star B star C is equals to A star B star C. So definitely associative property is satisfied. Now let us consider E is the identity element. So E belongs to D such that E star A, that is equal to A. Also A star E equals to A. Now E star A equals to A means E plus A minus 1 should be equal to A. So from here you can easily find out E equals to 1. 1 is also an odd integer, so definitely it is a part of D. Similarly A star E, that is A plus E minus 1, that is also A. So from here also you will find E equals to 1. So 1 is the identity element. Finally, we need to find out the existence of inverse. You can see C belongs to D. I have taken C as inverse element of A. So C star A will be C plus A minus 1, that is equal to 1. So from here C will be 2 minus A, because A is an odd integer. So technically if I want to find out 2 minus A, for example 5, you have taken A is equal to 5, so 2 minus 5, that is also odd. You have taken 3, that is also odd. Even if you want to choose A equals to minus 3, 2 minus of minus 3, that is plus 5. So every time whenever A is odd, then technically you can say 2 minus A is also odd. So it is also a part of D. Similarly A star C equals to 1 will give you the same result. That means you can say D comma star is a group. And finally you have to check the commutativity. A star B is equals to what? A plus B minus 1. Now addition can trivially satisfy commutative structure. So A plus B can be written as B plus A minus 1, but this is equivalent to B star A. So we can say this is true for all A comma B belonging to D. So the composition star ultimately forms a commutative group, and definitely you can say so D comma star is a commutative. This is the proof of this result. Now let us consider the next problem. Prove that the set of all rational numbers other than 1 forms a commutative group with respect to the composition star given by A star B is equals to A plus B minus AB, where AB belonging to Q minus singleton 1. That is, from the set of rational numbers you have excluded 1. Now A and B taken from Q, that means A and B are different to that of 1. A star B, A plus B minus 1, composition of two rational is also rational number. Now A plus B minus 1, definitely it is not equal to 1, because if it is equal to 1 then A plus B should be equal to 0. That's why you can easily understand, actually it is not equal to 0, I mean to say A plus B minus 1, we are claiming it is not equal to 1. What will happen? Whenever you are considering this structure is actually AB, A plus B minus AB equals to 1 means you can write this thing. So factorize this expression. In that case you will get A equals to 1 as well as B equals to 1. That means if this part is equal to 1, you are getting a contradictory result, because already you have assumed A and B, both of them are different from 1. So whenever A and B are not equals to 1, A star B, that is A plus B minus AB, is also not equal to 1. So technically we can say if A comma B taken from Q, or better to say Q minus singleton 1, then A star B is also belonging to Q minus singleton 1. So we can understand definitely for all A comma B belonging to what? Belonging to Q minus singleton 1, Q must be closed with respect to composition star. Now again we have to verify associativity. A star B star C can be written like this, so that you can apply A plus B minus AB. Say this is A, this is B. So A plus B minus AB. Now simplify this expression. Whatever you will get, that will be your final result. Now after that you have to verify the value for this one. I haven't calculated this one. I hope you can easily solve it. So associative property is trivially true. Every time you have to select from Q minus 1. E is the identity of this structure. So technically you can say E is also not equal to 1. So E star A equals to A will give you E plus A minus EA, that is equal to A. So from here you will find A cancelled, E into 1 minus A equal to 0. Because A is not equal to 1, only possibility is what? E should be equal to 0. So 0 is the left identity. In a similar manner, A star E equals to A will also give 0 is the right identity. So 0 is the only possible identity element. And finally, if A belongs to Q, we can say obviously Q minus singleton 1, then A not equals to 1, B also belonging to this one, this structure Q minus singleton 1, then let us assume that B is the left inverse of A. That means B star A should be equal to identity, that is 0, so that B plus A minus BA should be equal to 0. From here you can easily find out the value of B. So that is A by A minus 1. So this is the left inverse. Similarly, if I want to consider A star B equal to 0, the result will be A plus B minus AB equal to 0. So from here also you can see, if I want to consider value of B, that is 1 minus A, that will be minus A. So technically B will be A by A minus 1. Here also, as A not equals to 1, the structure is well defined, and so this is the required right inverse, and consequently you can say this is the inverse element. That means for all possible structures belonging to Q minus singleton 1, inverse element exists, and hence definitely this is going to be a group. Now finally we have to check the commutativity. So A star B is equals to this. Again I will say product and addition will trivially satisfy commutativity. So A plus B can be replaced by B plus A. AB can also be replaced by BA. That is also equal to what? B star A. So we can finally say this structure or composition is commutative, and hence Q minus singleton 1 is definitely a commutative structure. Now moving on to the next problem. G comma not be a group. Let us consider a mapping IA maps from G to G, given by IAX is equals to A inverse not X not A. Then we have to show that IA is a bijection, that is 1-to-1 and onto mapping, and also it is, you have to explain the fact whenever G comma not is a commutative group, what will happen. So let us consider x1 x2 belonging to G. I not x1 can be written by means of the given composition A inverse not x1 not A. Similarly, I not x2 will be like this. If possible, I not x1 is equals to I not x2, then these two things must be same. Now operate A from the left hand side on either expression, also A inverse from the right hand side from either expression. So A not A inverse not x1 not A not A inverse. Similarly from the right hand side, A not A inverse not x2 not A not A inverse. This part will be E, this part will be E. Similarly this part will be E, this portion will also be E. So that's why you will get what? x1 not E, that is x2 not E, but ultimately E is the identity, so x1 should be equal to x2. So whenever these two things are identical, we can say x1 is equals to x2. Contrapositively, if x1 and x2 are different, then definitely we can say I not x1 should not be equal to I not x2, and hence IA must be what? Injective. So actually you can say this is IA. So IA, as per our composition, it is IA, not, it should be IA. Now Y belongs to G. In order to check the surjectivity, we can choose any element Y belonging to G. Now Y can be written as, by our assumption, A inverse not X not A for some X obviously belonging to L, X belonging to G. Now A not Y, as usual, A not A inverse not X not A. A not Y will be E not X not A. A not Y will be E not X, that means X not A. Operate A inverse from either side, then this part should be equal to E. So A not Y not A inverse, that should be equal to X not E, that is X. Now this part can be written as A inverse whole inverse not Y not A inverse. So imagine this is A1. So the structure is what? A1 inverse not Y not A1. That means for each and every possible X belonging to G, we have a specific structure like this. So I have written the same thing here. Thus we can say, because G is a group, it is mentioned in the question. So for all A belonging to G, we must have A inverse is a part of G, and hence X is also a part of G. So we have seen for Y belongs to G, there must exist some element X belongs to G satisfying this type of structure. So IA must be surjective. Because IA is one to one as well as onto or surjective, so IA is a bijective mapping, or simply you can say IA is a bijection. And finally you can say, if G comma naught is a commutative group, then what will happen? If G comma naught is a commutative group, then IAX can be written as what? A inverse not X not A. This can be written as what? A inverse not A not X. Why? Because G is commutative, so X not A will be A not X. This is equal to E. Ultimately E not X will be X. That means IAX will be X. But this is true for all X belonging to G. So technically IA will behave like an identity mapping. So whenever we are considering the commutative structure, then you will see IA will behave like the identity mapping. So I have discussed few problems from the exercise of SK Mappa book, that is abstract algebra of SK Mappa. I hope you will find this solution useful and also prepare these problems very carefully. Thanks for watching.